Okay, so we're going to finish up chapter 10 today, this morning, and then we'll get into osmosis and dialysis lab. We've got some water already started, and we'll talk a little bit about that as soon as I finish introducing this topic. Let's see here. Let's get rid of this mess. Acids, bases, and salts. Unless you know chemistry and been introduced to this topic, acids and bases are probably familiar, but salts in chemical terms are probably foreign to you. And when we think of salt, we generally think of sodium chloride, table salt. Come on. There we go. All right. So there was a time when I was young, acids were introduced as having a sour taste. Bases would have a bitter taste. But we can't taste chemicals in the chem lab anymore, so that's out the window. So you could try vinegar, right? You know, that's an acid, what it tastes like. I
don't like the taste of vinegar.
You don't like the taste of vinegar? No. Not even on your salad?
No.
And if you're unfamiliar with the bitterness of base, all you have to do is get most medications now have a basic pH. And I'll tell you what pH is in a minute. They're basic. So if you don't swallow the pill whole, if you accidentally bite into it, it's going to be very bitter. All right, so we're going to talk about acids, bases, and then we're going to talk about what a salt is, and then we're going to talk about buffers. So that's the general progression for today's lecture. The first chemical concept that was widely accepted for an acid and a base was proposed by a Swede, a chemist from Sweden, 1884. His name was Arrhenius. So he did a lot of other stuff too. He's not known for just acids and bases, but his proposal was that an acid is any compound that when you put it in water will dissociate into hydrogen ions and what's left over. And the hydrogen ions are always positive. In fact, a hydrogen ion, in most cases, is just a single proton, because hydrogen has one proton, one electron. If you take away the electron, all you got left is a proton. So in most cases, they're the same thing, except for deuterium and tritium. And there are minor components, so we don't even consider them. So if I slip and call it a proton instead of a hydrogen ion, you know what I'm talking about. All right, so this was Arrhenius' definition of an acid. And we learned from our nomenclature that acids always have the dissociable hydrogen first. And then this part of the acid might have some other hydrogens, but they don't break out. They stay put. For instance, vinegar. Right? Vinegar only has one hydrogen that breaks apart. Right? These hydrogens are locked too tight. They won't come loose. All right, so this is Arrhenius' definition of an acid. His definition of a base says that a base has a hydroxyl group in it. And that hydroxyl group breaks off when you put it in water. So you have this plus, and then you have the hydroxyl. And we know hydroxyl as a polyatomic ion. Okay, that works for the vast majority of acids and bases. And the best example of that is lye. Like use sodium hydroxide to make soap, or use to clean out your drain, like Drano. They used to sell Drano as crystals, right? Pure sodium hydroxide, but OSHA and EPA must have got hold of them. Now you can only buy it in liquid form, like liquid plumber. That's sodium hydroxide. All right, so Arrhenius, while Arrhenius said that an acid has an ionizable hydrogen attached to it, at least one, and a base has a dissociable hydroxide attached to it, at least one, sometimes more. Now, the problem is that there are compounds that when you put them in solution, they make a basic solution. You can measure the hydroxide concentration, or you can use things like indicators to show whether it's acidic or basic. But the molecule doesn't have hydroxyl in it. And the best example of that is ammonia. If you put ammonia in water, it will produce hydroxyl ions. And so we need a new definition to account for these. And in fact, the one that's proposed by Johannes Bronsted and Thomas Lowry, independently of each other, so they both get credit. They decided that the best way was to focus on the protons only, on the hydrogen ions. And a Bronsted-Lowry acid is a proton donor, right? So this would be a proton donor, right? Give up its proton, but it has to go somewhere, right? If you're going to be a donor, you got to give to something. So in this case, Bronsted and Lowry. Okay, let me put them up here. So the Bronsted-Lowry, I think that's got a umlaut over it, doesn't it? No, it's I don't know what you call that. Bronsted-Lowry acid base definition says that you've got a proton donor. So rather than put that in water and just say it ionizes, we use water as a reactant. So now the proton, if it's just the acid in water, then the proton is donated to that water. So now we have this left over. And now we also have a new type of polyatomic ion called the hydronium ion. And this is a covalently bound compound. So all of those hydrogens have covalent bonds with the oxygen. All right, so this is a Bronsted-Lowry acid. So now we're gonna switch things around, and the base then is a proton acceptor. If we were to use something like, well, use our previous example like this, like that. Because when you put ammonia in water, then we transfer a proton from water over here, and now we get the ammonium polyatomic ion. And what's left over, after you take a hydrogen away from H2O, you get OH. Let's see. I lost my share, didn't I? There we go. So, whereas Arrhenius focuses on two independent functional groups, the hydrogen ions and the hydroxyl ions, Bronsted-Lowry focuses only on the protons. That way, now we can explain with Bronsted-Lowry's definition, we can explain all these oddballs plus everything that was covered by Arrhenius. And that's going to be good enough for our purposes for now on. Now, all aqueous solutions, this will work. Now, I'm going to introduce you to another concept for acid bases later, focusing on the electron transfer, but it's not as important. Most of our work will be focused on this concept: proton donor, proton acceptor. All right. So there's your acid, proton donor, or hydrogen ion donor, and acceptor for the base. All right, terminology. So if we have, notice what I've done here, without telling you I did it, was if this is the acid proton donor, water then is a base under this definition because it accepts the proton. Okay, and in this case, the ammonia is the base because it accepts the proton, and water is an acid. So water can be either one, acid or base, depending on its situation. Now, when we do this, we produce, on this side of the equation, we produce from this acid, now we get a portion of it that can accept a proton. So this is called the conjugate base. Of this acid. And this obviously will be conjugate acid. Of that base. All right, so conjugate, when we say conjugate acid-base pair, we're talking about this is the acid and that's the base. So this is a pair, acid conjugate base pair. Sometimes it's written like this. You'll have the acid here and then you'll have the base here. Okay? Two things are required, at least two, to be a conjugate acid-base pair. One, you have to have a proton donor. And then the conjugate base has to be this molecule with only one hydrogen missing. It has to have this portion of the molecule or extra hydrogens, because you only do one hydrogen at a time in this reaction. You can't do 3 or 4 hydrogens all at once. One at a time. So if this loses a hydrogen, now it becomes this conjugate base. If you have a diprotic acid, another 2 hydrogens, or a triprotic, the dissociation occurs one at a time. So for instance, if we have sulfuric acid plus water, right, then you remove one of those hydrogens, it goes to this hydronium here, and what you have left over is HSO4 minus. Because you lost a positive, it left behind its electron. Now you've got a negative here with a hydrogen. This is an acid-base pair, conjugate acid-base pair. Then this one can also undergo an ionization with another water molecule. So now you have the sulfate polyatomic ion plus another hydronium. In this case, that's the acid, and this is the conjugate base. So the acid-base pair is this one and that one. In our example here, the conjugate acid-base pair would be HF, hydrofluoric acid, and the fluoride ion in solution. Like that. Okay? All right. I mentioned earlier that in this circumstance, water is an acid. Let's see. In this case, it's a base. In this case, water is an acid. You can go either way. That's called amphoteric or amphiprotic behavior. It can go either way. And in fact, if you have pure water, you can have two water molecules encounter one another. One of them becomes an acid and the other one becomes a base. So let's say this is the acid and this is the base. So a proton transfers over here and you get what's left over here from the acid is a conjugate base. And what you have from the base is a conjugate acid. That does happen in water. Not very much of it. Most of it's still over here. Just a tiny amount does that. Okay. So when we name things, I used the names earlier without telling you what they were. Monoprotic acids have one hydrogen that can ionize. Only one. Diprotics have two, like sulfuric acid. Triprotics have three, like phosphoric acid, H3PO4. So it can undergo three processes. It can do one, two, and then a third one. One proton at a time, always. And then we lump anything bigger than a diprotic into polyprotic, if you just want to say that. So you've got a mixture of sulfuric acid and phosphoric acid. You say, my mixture contains polyprotic acids. Now, the chemical definition of strong and weak. Talk about that for a minute. Strong to a chemist means almost 100% ionization of the acid. An example is hydrochloric acid. So hydrochloric acid in an aqueous solution will be almost 100%. In fact, for all intents and purposes, is 100% this direction. So you would have the chloride ion left over, and then you would have your hydronium ion. Right. And very, very little, if any, return. That's the definition of strong in chemistry. Normally, what we think of when we say strong acid is something that'll burn you. But in fact, weak, let's talk about weak. A weak acid is one that does not dissociate to a large extent, like acetic acid, vinegar. That's why you can taste it, because it won't burn your tongue off. Not at those concentrations. So then we have this reaction where we have C2H3O2, the acetate ion, plus our hydronium ion. And this is mostly back over here. Very little of it goes over here. Maybe we can quantify it. Okay, that's the chemical definition of strong versus weak. Now, from a safety standpoint, if this strong acid is only 0.01 molar concentration, it's probably not going to do much damage, right, if you spill some on you. Whereas if it's 1 molar, yeah, it'll burn your skin. This weak acid, if it's 0.873 molar, which is 5% weight volume for vinegar, right? It's not going to hurt you if you spill some vinegar on you, right? Unless you got to find a cut, right? Then you'll feel it. But in the laboratory, in fact, I think we've got some back here. I used to use glacial acetic acid. Glacial is a grandfathered in term. It just means 100% acetic acid. 100% acetic acid will take your hand off. It's a weak acid, but it's so concentrated, it has enough of these as a consequence. In fact, it doesn't have any of these because there's no water there. So anything that's there has to occur from ionization of this into that, plus, well, it just reacts with your skin. Actually, what happens is if you immerse your hand in 100% acetic acid, then it starts dissolving into the water in your tissues, right? And it's going to produce a lot of this because it's so concentrated, and that does the damage. So it's a little complicated. Anyway, the point is that strong and weak in chemical terms doesn't mean the same thing as our common understanding of strong and weak. We had a slide a minute ago with hydrofluoric acid. We used to use, let's see what it was. I think it was 37%. No, it was higher than that. It was concentrated hydrofluoric acid, which is extremely dangerous for 2 reasons, right? It's a strong acid. Well, actually, it's a weak acid, but at those concentrations, it's strong enough. Plus, the fluorine interacts with your tissues and with your bones. So if you drop some of that on your hand, it'll just keep eating until it comes out the other side. So we used to double glove when we played with that one. And we had to use it sometimes because I was dealing with digesting soils. And sometimes hydrofluoric acid is the only thing that will attack certain minerals in the soil. So let's move on unless there are questions or comments. These are typically encountered strong acids, right? Hydrochloric, I already mentioned. Hydrobromic, hydroiodic. In fact, the further down you move in that column, in the halogens, hydrochloric is stronger than hydrofluoric. And hydrobromic is pretty strong too. Hydroiodic is strong. Then we have some polyatomic acids. The nitric acid is a very strong acid. Chloric acid and perchloric acid, they're both strong. In fact, perchloric acid is extremely strong, and it's dangerous. In fact, with organic compounds, it's explosive. If I put, I don't know if I've told you this before, maybe when we were naming acids. If you take perchloric acid, like we used to use 70%. If you take perchloric acid in a beaker and then drop a nice big pat of butter in it and set it on your hot plate in the fume hood, turn it on high, pull the sash down, and evacuate the building because it will blow. So what we used to do is take nitric acid with our tissue samples and put some nitric acid on them on the hot plate and let them sit cold all night. Do a pre-digestion. Then we could put perchloric acid in there on top of that and finish the digestion, and it was perfectly safe. Sulfuric acid, right? Sulfuric acid, you can get it 98%. Right, we've got some in the cabinet back there. 98% sulfuric acid is extremely concentrated and very heavy. Okay. One caveat with these polyprotic acids, the only ionization that can be considered strong is the first proton. After you dissociate one proton, let's use sulfuric acid as an example. Once we ionize, right, and we get HSO4 minus plus the hydronium ion, that's the strong. So it's going to be all the way over to the right. But this one is weak in chemical terms. This is a weak acid. And actually, it just stands to reason, right? If we're trying to remove a proton from a neutral compound, it's a lot easier than it is trying to remove another proton from a negative charge. Right? It's more difficult to pull it loose. So this one's weak, that one's strong. And that's typical for strong acids. If it's polyprotic, then the first one is the only one that's strong. All right. Let's see. All right, but we've already talked about that. And differences strong and weak acid. This comes straight out of your textbook, so I'm not going to spend a lot of time on that one. Bases. We use the same concept for bases. Strong means completely dissociated. So all of the group 1, the alkali metal hydroxides, lithium hydroxide, sodium, potassium, rubidium, cesium hydroxide, they're all strong. In other words, they completely dissociate in solution. The alkaline earths are the only ones that are strong there are calcium, strontium, and barium. And there's another caveat here. When we say calcium hydroxide is strong, first you got to get it into solution, and it's not very soluble. But whatever goes into solution completely dissociates. Okay, so you can't get the concentration very high, but what does go into solution will completely dissociate into those ions. Okay. Strong acid, when we place a strong acid in water, what's it going to look like? Well, we're definitely going to get the hydronium plus the anion left over. But the difference, the key difference is in the equilibrium, those arrows. B would be the one for the strong acid. Right? The arrow is a lot bigger, but we're trying to show the difference there. And the return is very small, if at all. Okay. We can express this equation where we watch the ionization of acid in water. We can express that as an equilibrium equation. And let me take a peek at my hard copy so I don't steal my own thunder. We talked about equilibrium earlier, didn't we? In a previous chapter? Okay, good. Okay, this is a special equilibrium for acids, and its equilibrium constant is Ka. Very inventive. So we set it up just like we did earlier equilibrium equations. In the numerator, we have the products. So in this case, we'll have a concentration of hydronium ions. We'll also have a concentration of the conjugate base of the acid. Okay. Then in the denominator, we'll have the the non-ionized acid. Now, notice what's missing. Water. Water is a pure liquid. We don't put it in there. Right? By convention, equilibrium equations don't have pure liquids in them. They don't have solids in them. Only things that have a potential for changing concentration. The concentration of water is not going to change in this reaction. So this is the acid dissociation constant, or the acid ionization constant, the equilibrium constant for the acid. Now, if it's a strong acid, right, this is going to be almost infinity, because that's going to be huge, huge, and very, very small. In fact, if this is very close to zero, we might as well put an infinity there. So acid ionization constants for strong acids don't mean anything. They're very high, if not infinite. There's another expression for the strength of an acid. We can base it upon percent ionization. In other words, all we need to do is know this concentration and that concentration, and we can calculate that concentration over this concentration and times 100 will be percent ionization. I don't know why they call it percent dissociation, because it's not dissociated, it's ionized. I don't have an answer for that one. This one is a constant. For a given temperature, it's going to be constant no matter what these values are. These values are going to change in order to give you that constant value. Right? They'll be at different positions. Right? You may have a large amount of this. You're going to have a large amount of this, enough of this to give you that value, that same constant. It's a constant. But the percent ionization varies with the concentration. So if you, as a matter of fact, when you increase the concentration of your acid, the percent ionization goes down. It gets less. Now, if we're talking about weak acids, then the stronger the weak acid, the bigger this number is going to be. So the Ka is going to get bigger as the weak acid gets stronger. If we like have a list of different acids from weak to strong, then as you move down the list, the Ka is going to get bigger. The percent ionization also increases with this one. So if we're trying to compare different acids, and we say, okay, the acid gets stronger as we increase this value, and for any given concentration of the acid, the percent ionization is also going to increase, simply because we're making this one bigger and this one smaller. But if you're talking about a single acid, then as you increase the concentration of the acid, this value goes down. So there's a distinction between comparing different acids versus comparing a single acid at different concentrations. You can do the same thing for a base. So if we have anything that we call a base here, let's use our example. Let's use ammonia. Say if we have ammonia here, right, it's going to be the base, water is going to be the acid, and we're going to set up an equilibrium here with the ammonium ion and the hydroxyl ion. So we can write an expression for the K for this one would not be Ka, but Kb. So what we do is we take that value for the ammonium ion concentration, the hydroxyl ion concentration, and the ammonia concentration, and leave the water out because it's a pure liquid. And that would be our expression for the KB. So notice if we were to start from here and if we somehow put ammonium ions into solution, which you can do, like ammonium chloride would go into solution. The chloride won't react with water because HCl is a strong acid. Once it produces the chloride ions, they don't want to go back. Right, so you got ammonium in solution. Now what does ammonium react with? It doesn't react with hydroxyls. It reacts with water because there are very few hydroxyls in there to start with. So it transfers as an acid, it transfers to water, and you get a Ka. It's a different expression. It's not the inverse of this one. The Ka and the Kb are not inverses of each other. That's one common error that students make. All right. So now that we've defined acids and bases, let's talk about salts. Up to this point, we've only discussed individual acids, put them in water, or individual bases, put them in water. Now we're going to react an acid and a base. So when you do that, we're going to use the Arrhenius type acid base. So let's use a real example. We've got a strong acid here and a strong base, hydrochloric acid, sodium hydroxide. When they react, they're both strong. So the reaction is going to send them all the way over here. What we actually have is a double replacement reaction. That sodium replaces this hydrogen. So sodium and chloride associate. But we know they're completely soluble, so it's really sodium ions and chloride ions in solution. But what we have with the hydrogen replacing the sodium, you get HOH. That. Okay? So whenever you react an acid with a base, you get water, and then you get the chemical definition of salt. In this case, the salt is table salt. But any acid, any base react gives you a salt and water by the chemical definition. So if we had, let's see, potassium chloride and sodium, not potassium, nitric acid. The nitrate would associate with sodium and be sodium nitrate. That would be the salt. Cation and anion together from an acid-base reaction is the salt. Now, sometimes, not a lot, but sometimes when you get the cation from here and the anion from here associated with one another, they might be insoluble. They'll drop out of solution, right? How do we tell? Well, we use this chart right here. Right? Cations across the top, cations down the side. So let's see if I can figure one out. Let's see, how about barium hydroxide and sulfuric acid. That would produce barium sulfate as the salt. And barium sulfate is insoluble. Just drops out of solution. Right? That's why they use barium sulfate for enemas. Right? When they're going to do x-rays of your lower intestines, they'll give you a barium enema. It's barium sulfate. Barium is a huge atom, and it makes a nice shadow with x-rays because it absorbs x-rays very efficiently. So they fill you up with that stuff and take an x-ray, and they can see all the little undulations and pockets or anything that are in your intestines. But it's not toxic because barium sulfate is insoluble, right? None of it gets into your system, right? Once it goes in and they get rid of their x-rays, then you got to expel it. Okay. This is known as a neutralization reaction. When an acid and a base react, they neutralize one another and they produce a salt and water. Now, when we have a polyatomic, polyprotic, or polyhydroxic base, when you react those, we show the overall reaction, H2SO4 and KOH, right? But it more than likely, it occurs in steps, just like the ionization of an acid. But if they're both strong, like, well, sulfuric acid is strong for the first proton and weak for the second one. But KOH is a strong base. So what's going to happen is it's going to take that second proton off of the HSO4 minus. It's going to take it off really easy. It's just going to rip it right off of there. So this overall reaction is accurate. Now, when we talk about, let's see, I mentioned earlier, I drew the equation where water reacts with water to produce hydronium and hydroxide. This is the reaction in reverse, where you get hydroxide ion, hydronium ions, and they produce two water molecules. Right? Hydronium is the acid, hydroxide is the base. We transfer a proton over to the hydroxide, makes water. We lose a hydrogen from hydronium, and that makes water. So in a neutralization reaction, you get water and a salt. That reaction I showed you with water and water is called self-ionization. And water does it, and other chemicals do it also. My background is in agriculture. A lot of farmers, when they have the equipment, find it more economical if they have to put nitrogen on their crops, especially things like corn, which really uses a lot of nitrogen. One of the more effective ways and economic ways is to inject anhydrous ammonia. That is, it's pure 100% ammonia. So all your equipment has to be stainless steel. And you have to have injector blades that go down into, you plow your field and do whatever you're going to do to it. And then you take this thing and pull it behind your tractor. You got to probably have the injectors first, and then behind it you have the stainless steel tank full of ammonia, and it's pumped into those injectors, and they inject it below the ground where there's moisture. Right? If there's no moisture, then that ammonia just goes and it's gone. So you have to inject it down into the soil. But in that tank of pure ammonia, you get one ammonia molecule finds another ammonia molecule and transfers a proton. This is the acid. This is the base. Now you get, let's see. Is that right? Yeah. NH2 minus plus NH4 plus. So water is not the only molecule that does this, self-ionization. It happens with lots of other things. Water is the most important one because most of our chemical reactions, if we don't do them as solid with solid or gas or other types of mixtures, are in aqueous solution. Right? And in fact, all the reactions that occur in here are in aqueous solution. All right. Now, when we write that expression, let's just replace these with water. when we write this expression, we can also write an equilibrium constant for that expression. Now we know that it's going to be very small that way and very big this way. But it has a special equilibrium constant, Kw, and this is a pure liquid, this is a pure liquid, so those two terms, we don't even put them in. All we have is the numerator. We have the hydronium concentration and the hydroxyl concentration. And that is the equilibrium constant for water. And at 20 degrees, the equilibrium constant for water is times 10 to the minus 14. So it's extremely small. Now, whatever else happens in aqueous solutions, this is always happening with it. If we mix in a strong acid in an aqueous solution, then the reaction of the strong acid is so, or even a weak acid with a larger equilibrium constant, it overwhelms this. So it dominates, and this is insignificant, but it does still happen. It's still there, always. And this value will change with temperature. Now, just as a, let me point this one thing out. If these two values come from that reaction, and it's pure water, right, what would the concentration of that and that be in order to give us this value? They would have to be equal, wouldn't they? Right? Because it's 1 to 1 to 1 to 1, right? So what times what gives you 10 to the minus 14? In the minus 7, right? So all you do when you multiply these together is you add the exponents and you get 10 to the minus 14. Okay, that's why in pure water, this is neutral. No acids, no bases in there. This is what you measure in a neutral solution. 10 to the minus 7 molar concentration. Now, like I said in a previous discussion of equilibrium constants, we don't put the units here. And for equilibrium constants, simply because the sky's the limit. You can have all kinds of combinations of units and powers. So it would just be a mess. We just have to be extra careful that we use the correct formula. And when we do our calculations, we get the right answer. We'll notice also that since this is happening all the time, if we put an acid in that solution, like hydrochloric acid, and we increase this value, right, this 10 to the minus 7, then increasing it would be like 10 to the minus 6, or 10 to the minus 5, or 10 to the minus 4. It's getting bigger. If we make this one bigger, say if we make it 10 to the minus 6 by adding a little acid, this one has to be 10 to the minus 8 to give us 10 to the minus 14. That's what I mean by this is always happening. So they go opposite to one another. This one gets bigger, this one gets smaller, and vice versa. Now, if they're both 10 to the minus 7, then it's a neutral solution. But if we make this one bigger, that's an acidic solution. If we make this one bigger, that's a basic solution. So that's what we're saying. If they're equal to one another, then it's a neutral solution. If hydronium is larger than hydroxyl, it's acidic solution. If hydroxyl is greater than hydronium, then it's basic solution. And that happens even at different temperatures, right? If we increase the temperature here, then these values will increase. Both of them will be the same value, but bigger. So this value will also change, but they're still equal to one another. So even if we heat water up, if there's only water in there, it's still neutral because hydronium and hydroxyl are exactly equal. Okay. Let's try solve a little problem here. Calculate the hydronium and hydroxyl as required for each of the following solutions at 24 degrees. Actually, 24 degrees, the 10 to the minus 7, 10 to the minus 7 equals 10 to the minus 14 occurs at 24 degrees, not 20 degrees. So that's why we're given 24 degrees here. So for A, I think I need a new one. For A, we have 1.0 times 10 to the minus 4 molar hydroxyl concentration. Is this neutral, acidic, or basic? Well, if it were neutral, that would be 10 to the minus 7, wouldn't it? But it's not. It's a whole lot bigger. That means this one has to be basic. So what would the hydrogen ion concentration or the hydronium ion concentration would then be? In this solution, 10 to the minus 10 molar. Because that one times that one equals 10 to the minus 14. Okay. How about B? 2.0 molar hydronium. That's definitely bigger than the hydroxyl. Hydroxyl is almost non-existent in this solution. So this one would be acidic. All right. Now we can calculate what the hydroxyl ion concentration is. All we need is Kw equals 1 times 10 to the minus 14, which is equal to hydronium and hydroxyl. So if we put that 2 in here, right, divide that into this, so that'd be 1/2 times 10 to the minus 14 equals, wait, minus. So this would be 0.5 or 5 times 10 to the minus 15, right? Molar hydroxyl. Almost non-existent. It didn't ask us that, but I throw that in there for laughs. There we go. So that one's basic, and that one's acidic. All right. Now, we've been working in molarity up to this point. Right. All those equilibrium expressions, concentrations are in molarity. But there was a Danish chemist, name was Sorensen. For some reason or other, he was working with these small concentrations. So it's always 10 to the minus 10 or 10 to the minus 15 or 10 to the minus 3 or something like that. He just got tired of using those scientific notations for all of these concentrations. He wanted something that he could with more compact. So he used a mathematical formula. He would take the, if he took the log, let's say we have a neutral solution. Now, I'll also say this. This is not what actually happens in water, but for convenience, we're going to use that equivalence, right? Hydrogen ions never sit out alone in water. They're always attached to something. But the calculations are the same whether you use this one or this one. So for convenience, we often write it this way. Okay, just so that's not confusing. Any more confusing than it already is. So what Sorensen did was he took the hydrogen ion concentration and he said, all right, what if I take the log of it? And this is log base 10, the common log, right? Everybody knows logarithms. Remember how to work logarithms? If you have a number and you take the log of it to base 10 and it equals some other value, say x, what does that mean? That means the log of a is 10 to the x power. Or a equals 10 to the x power. Okay, that's what that means. All right, so if you take the log of this number, let's say it was in a neutral solution. We got 10 to the minus 7 molar. If you take the log of that, what do you get? Well, 10 to the minus 7, 10 to the 10 to the minus 7 would be minus 7. Okay? But he didn't want negatives either. So he said, okay, this is a purely mathematical expression. I just take the negative of both sides. Okay. Now, the negative log of that value, which is the hydrogen ion concentration, the hydronium ion concentration, negative log of that is pH. Little p, capital H. It's not capital P, capital H. It's not little p, little h. It's not big P, little h. It's little p, big H. That's pH. Anything else is wrong. Okay. So that way he could express these large numbers and you could have the coefficients with them also. So you're going to need a calculator that does logs for you. Or before calculators, we have to use tables. Logarithmic tables. So I was kind of glad to see calculators come along. Okay, so let's see, do we have a, no, we don't. I was looking to see if we have, what am I missing? Let me do it this way. Let's say we have this linear scale. Okay, right in the middle is neutral. In this case, the hydrogen ion concentration is equal to the hydroxyl ion concentration. And at 24 degrees Celsius, that is equal to 10 to the minus 7 for both of them. What would the pH be? Well, if we use molarity on this scale and pH on this scale, that would be a pH 7. Okay? Now, what if we increase the concentration of hydrogen ions here? Increase hydrogen ion concentration. Say we went up to 10 to the minus 6, right? 1 order of magnitude. Everybody know what an order of magnitude is? It's a power of 10. So we won't go up 1 order of magnitude here to 10 to the minus 6 molar for the hydrogen ions. What's the pH? 6. Do the same thing for 10 to the minus 5, pH 5. 10 to the minus 4, pH 4. And we usually stop at 1. 10 to the minus 1 is a 1 pH. Now, this expression, this Sorensen's equation, is math. So you can put any concentration you want to in for the hydrogen ions. You could go past that, right? You could go 10 to the second molar or 10 to the first molar. If we did 10 to the first molar, then what would the pH be? Minus 1. Right? But when you get that high, it doesn't have much meaning. So and we usually stop at 1 on the acid side. On the base side, right, if you have a hydrogen ion concentration here of less than that, say 10 to the minus 8, this is a pH 8, 9, 10, 11, usually stop at 12. Okay, so on this side, we've got basic. On this side, we've got acidic. So as the pH value gets smaller, the solution is more acidic. And as it gets bigger, it's more basic. Okay? All right. So what would the pH be for 1 times 10 to the minus 4? Negative log of 1 times 10 to the minus 4 molar equals what? Well, remember your rules in logarithms, right? If you take the log of a product, it's the same as the log of this value plus the log of that value. So what's the log, say negative here? What's the log of 1? Well, it's 10 to what power is 1? 0. All right, so this one's 0 plus the log of 10 to the minus 4 would be minus 4. So minus 4 and 0 is minus 4, and a minus is a plus, so that's equal to 4. 4 pH. Okay? So that first one is a pH value of 4. Let's see. Get that up out of the way. Did I skip one? I did skip one, didn't I? Maybe I got them out of order. I think I did. I got them out of order. There we go. So what's the pH for if you have a hydroxyl ion concentration of 0.04? So the hydroxyl ion concentration is equal to 0.04. Okay. Well, we can't calculate pH until we know the hydrogen ion concentration. So if we know Kw equals 10 to the minus 14, and that's equal to hydrogen ion concentration times hydroxyl ion concentration, then we can fill this one is 0.040 and solve for this unknown. So hydrogen ion concentration is 10 to the minus 14th divided by 0.04, which is 2.5 times 10 to the minus 13. Now that's hydrogen ion concentration. So we can take the negative log of this value, and that's where we get the pH of 12.6. Notice for significant figures, how do you calculate significant figures? Well, actually, do two here. Okay. When you're calculating a logarithm, you look at the coefficient. How many significant figures are in that coefficient? 2. When you finish the calculation, those 2 become the number of decimal places in your logarithm. So 2 significant figures here means 2 decimal places in the pH value. That's why 12.60 is correct. All right? Okay. What's the pH of a solution if the pH is 5.85? Right? If we have a pH of 5.85, what is the hydrogen or the hydronium ion concentration for that solution? Well, this is pure math, right? This is equal to the negative log of the hydrogen ion concentration, right? So we can't resolve this logarithm as long as there's a negative in front of it. So we get the negative on this other side. Minus 5.85 equals the log of the hydrogen ion concentration. Now we go back to our definition for logarithms with this 10 down here. That concentration is equal 10 to this power. Okay? So 10 to the minus 5.85. Now, how do you do that on your calculator? Well, let's see. On mine, I got a log key for log, and then shift above it, or function key above it, is 10 to the x. So I hit the function key and hit the log key, and that gives me 10 to the x. And if I put 5.85, change the sign, right? And then I hit 10 to the x, I get, let's see, 2 decimal places. That means 2 significant figures in my answer. So my answer is 1.4 times 10 to the minus 6 molar. Here we go. Okay. That's how it's done. Now pH has meaning in chemistry, but the calculation itself is pure math. There's nothing special about that. All right. So this I already told you this. pH greater than 7 is basic, less than 7 is acidic. And these are some pHs of some common things. Let's see. It doesn't have stomach acid in there. It's just vegetables, it looks like. Vegetables, fruits, and stuff. All right. So limes are really acidic, 1.8 to 2. Actually, your stomach acid is between 1 and 2, depending on the meal. Right? If you eat a meal that's high in tomatoes, like spaghetti sauce or pizza, the pH is going to probably drop down close to 1. But normally it sits around 2, 2.5. So the correct mathematical expression for pH is that one right there. Nothing magical. That's just it. That's what Sorensen invented. Now, since pH calculation is strictly mathematical, we can do the same thing to hydroxyl concentrations. Right? Somebody decided, well, Sorensen said it was okay for hydrogen ions. How about hydroxyls? So if we know the hydroxyl ion concentration, we can take the negative log of that. So guess what that's called? POA. Okay. We can do the same thing for the K values too. Right? If you have a K, A for the acid, and you take the negative log of that, then the value is going to be pKa. Or if it's Kw, log Kw equals pKw. We can calculate that one because we know this one is 10 to the minus 14, right? So that value would be 14. pKw is 14. Now, if we take the whole equation for Kw, right? We know that Kw equals hydrogen ion concentration, or hydronium, hydroxyl ion concentration equals 10 to the minus 14, and we take the negative log of that entire equation. Okay? So what's the negative log? If we take the negative log of a product, remember what that is? the same thing as the negative log of this one plus the negative log of this one. That's an identity, they call it, for logarithms. And then the negative log of 10 to the minus 14. So this would be, negative log there would be pH. Negative log here would be the OH. And the negative log here would be 14. So the pH plus the POH equals 14. Now we're getting something that's a lot easier to handle. Remember back when we calculated the hydrogen ion, the pH, when we were given the hydroxyl ion concentration, we had to go a couple of steps. Now, all we have to do with the hydroxyl concentration is calculate the POH, subtract it from 14, and we got the pH. All right. Very useful equation. The pKa for HF, hydrofluoric acid, is 6.8. Actually, the Ka for the acid is 6.8 times 10 to the minus 4. Right? That's not a strong acid. But we can calculate the pKa for that. And it's 3.17. The thing about pKa's, when we calculate pKa's for weak acids, they run inverse to the Ka's, just like our pH scale. So the smaller the pKa, the stronger the acid. If we have a pKa of some acid at 10, it's a lot weaker than HF. Okay. Let's see, what's this one about? What's the pK? If the Ka is 6.3 times 10 to the minus 4, what's the Ka, and is the solution acidic or basic? All right. So we've got a Ka of 6.3 times 10 to the minus 4. Molar. We take the negative log of it, equals what? Let's punch in the equation in the calculator. 6.3 exponent negative 4. And then we take the log of that and change the sign. So I get 3.2. 3.20. Right, two significant figures. 3.20 equals the pKa. Under standard conditions, yeah, 3.20 is the pKa. So it's either C or D. And this pKa is less than 7. So this is going to be an acidic solution. All right. We can treat the pKa like we do pH. If the pKa is less than 7, it forms an acidic solution. If it's greater than 7, then it's going to form a basic solution. All right. You see how much time I got left. How many more slides we get to go? We got a few. All right. So what about salts? When you put a pure salt into solution, what happens? It depends on what the salt's made of. As long as the salt is soluble, it's an ionic compound. As long as it's soluble, then the potential is for the cation to react and the anion to react with water. That's a process known as hydrolysis. It could produce hydronium ions or hydroxide ions, or both. It depends on what it's made of. So if we have a salt that's made from a strong acid and a strong base, look what happens. Sodium chloride, for instance. You put sodium chloride in solution, what is it going to do? It's going to dissociate into sodium ions and chloride ions. I need another marker. All right. Now, when these get dissociated, they're in intimate contact with water molecules. Right? So what could happen? Well, sodium, if it reacts with water, right, it can't donate a proton, so could it accept a proton? Theoretically, it could accept a proton, and that would yield, actually, it wouldn't accept a proton. It would accept a hydroxyl, because the hydroxyl is the negative. So it could go to that plus this. But is that going to happen? The answer is no, because sodium hydroxide is a strong base. It completely dissociates to sodium and hydroxyl when you put it in solution. So that means that sodium doesn't want the hydroxyl back. Okay? Since it doesn't want the hydroxyl back, it's not going to take it from water. So this reaction doesn't occur. Similarly, chloride ions in intimate contact with water, we could say maybe this would happen. Is that going to happen? Well, hydrochloric acid is a strong acid, right? So this is completely dissociated to that plus hydrogen ions when you put it in a solution. So that chloride doesn't want any more protons. It doesn't want a proton from water. It's not going to get one. So that doesn't happen either, right? So what happens when you put the salt of a strong, that's made from a strong base and a strong acid? Nothing. The water stays neutral. Okay? That's the whole point of that one slide. Strong acids, strong bases, when they make a salt, if you take that salt in pure form and add it back to water, you get no reaction. It's neutral. All right. Now, so to answer these questions, when you add a salt to water, you look at the origin of each, the cation and the anion. Where did it come from? So if we say ammonium chloride, put that in solution, it's going to dissociate into ammonium ions and chloride ions. Okay? All right, now what happens? Well, we've already said the chloride's not going to react with water. Just won't do it. All right, so there's no effect from that. But ammonium was the product of ammonia plus water, which is a weak base. Right? So it wants to be way over here. Okay? So in order to do that, it would need now to react with water. We put it in water, it reacts with water, and it donates that proton to the water. So now we have this instead. So when you put that in water, it reacts with water, it goes way well over this direction, and it produces an acidic solution. Okay? It produces an acidic solution because of the conjugate acid of that base. Oops. Sorry. So that's the chemical reason for the production of an acidic solution from this type of arrangement where you have the product, this salt is the product of a strong acid and a weak base. Okay, that's the chemistry. But rule of thumb, if you have a salt that's made from a weak base and a strong acid, it's going to produce an acidic solution. So the flip side would be something like this: sodium acetate. Sodium acetate, C2H3O2. What is it going to do? Well, it's going to dissociate into sodium ions and acetate ions. Okay? We already determined that sodium's not going to react with water, but acetate comes from a weak acid, acetic acid. It wants to be way over here. So C2H3O2 plus like that would be the weak acid formation here, right? But if we put this into water, now it has the opportunity, since it wants to be way over here, it wants that proton really bad. And where is it going to get it? It's going to take it from that from that water molecule. So now what you get is it works its way back by taking a proton from water. And now what you got left is hydroxyl ions plus that acid. So the product, when the salt is made from a strong base and a weak acid, then you get a basic solution. So a rule of thumb is strong base, weak acid to make the salt gives you a basic solution when you put the salt in water. Now that's the rule of thumb, but this is the chemistry. The basic nature of that solution is not due to the strong base. It's due to the weak acid, because the weak acid extracts a proton from water and leaves hydroxyls. Okay. Now, when you have a weak acid and a weak base forming the salt, then it gets a little trickier. It just depends, right? Which one wants a proton or wants to give up a proton worse than the other one? And when you do that, you have to compare the Ka of the weak acid with the Kb of the weak base. And whichever one is bigger determines whether it's acidic or basic. All right, but we're not going to go into that detail. We do in general chemistry, but not in here. That's too much depth. I might drown a few of you. So, some salts hydrolyze when placed in water. Salt dissociates in water to produce hydronium ions, hydroxides. When salts of a strong acid and a strong base are placed in water, the resulting solution is neutral. Okay. Now let's talk about buffers. What's a buffer? Whenever I hear that word or ask the question, my mind goes straight to Godfather, Part 2. All right. When I forget the guy's name, he was testifying before Congress, and somebody said, so you kill at the behest of your superior. And they asked him, did you ever get a direct order from Michael Corleone to kill somebody? He said, no, sir. There were lots of people between us. You mean there was a buffer between you and Michael Corleone? Says, yeah, the family had lots of buffers. What that means is there's something in there in the solution for our application, something about the solution that keeps the pH from changing. A buffer does that. A buffered solution in this context is one that will accept acids or bases added to it, but the pH will not change very much. It will change, but only slightly. That's a buffer. Most buffers, not all, but most, are composed of a system where you have a weak acid and its conjugate base. So, for instance, if we have an acetate buffer, we'll have, let's see, acetic acid. And I'm gonna simplify this. Rather than write the water that it transfers to, we're going to treat this as simply ionization. We know this is not the chemistry, but for our discussion and for calculation purposes, it works just fine. So we know that this equation, this equilibrium, wants to be way over here like this on that side. Okay, so here we have a weak acid and its conjugate base. Now, one thing I haven't told you yet is that the relationship between the strength of the acid and the base. If the acid is weak, the base is going to be strong. So what do we mean by that? Well, a weak base doesn't want to dissociate, doesn't want to give up its protons. But a strong base wants those protons. A base wants to accept protons very much. So if it doesn't give up its hydrogen ions very easily, then it does want to be back this direction. So it just stands to reason. Weak acids make strong conjugate bases. Strong acids make weak conjugate bases. All right, so we have a mixture of this acid and that base together in the same solution. That makes a buffer. When you add base to it, what happens? Well, if I add base to this solution, it's going to react with these protons. Right, and make water. So what happens when that happens? Right, we haven't talked, or we did talk about Le Chatelier's principle, didn't we? Last week. Didn't we? I think it was the last thing on the menu. Yeah, okay. So Le Chatelier's principle says, if we remove those hydrogens, make water out of them, which way is the reaction going to shift? It's going to go to the right. It's going to try to replace those hydrogens, right? So when we add a base to replace those hydrogens, we've got this weak acid to give up enough hydrogens to replace them and reestablish equilibrium. That means that we've removed the hydrogen ions and we think, well, maybe it's going to go basic, but it doesn't. Because now this weak acid is going to replace those hydrogen ions. Right, so the pH doesn't increase that much. What if you add an acid? If you add an acid, that means you're increasing this one. And this is a strong base. So any acid you add to it is going to be picked up by that conjugate base and shifted that direction until you reach equilibrium again. So it doesn't matter which one you add, acid or base, the pH is not going to change that much. Okay, that's the nature of a buffer. And this slide is exactly what I just told you. It's all a system of equilibrium. You've done something to disturb the equilibrium, and the system reacts. Now, this only happens when you have enough of this and enough of that together. so that you can get either one working. And there's an ideal concentration that allows you to do that. And we're going to talk about it in just a second. So that was add a base. This is add an acid. And there were a couple of scientists. One was Henderson. Henderson first proposed this modification. Right, here's the generic acid dissociating, actually ionizing, into a proton and conjugate base. Right? So if you write the Ka for that reaction, this is what you get. Well, Henderson was interested in calculating the hydrogen ion concentration of a solution. Right, so he solved for the hydrogen ion side, and that's what you get. Right? You can solve for the hydrogen ion concentration if you know the Ka for the acid, you know the undissociated or the unionized acid concentration, and you know the conjugate base concentration. Then you can find out the hydrogen ion concentration with those factors. Hasselbalch came along. Henderson did this work before Sorensen invented pH. Right, so that's where it stopped for Henderson. Then after Sorensen invented pH, Hasselbalch took that transformation and he said, okay, I'm going to go in here and do that negative log thing to Henderson's equation. So he took the negative log of both sides, just like that. So we see on the left-hand side, the negative log of hydrogen ion is pH, and the negative log of Ka is pKw, or pKa, excuse me, pKa. Well, we've got an unresolved quotient in the last term that we can't do anything with because we don't have a value for it, right? And we could resolve it out into, right, the log of a quotient is the log of the numerator minus the log of the denominator, but that doesn't get us anywhere. So Hasselbalch said, I'm going to leave that one alone. Right, so that's what happened next. pH, pKa minus log of HA over A minus. So the unionized acid divided by the conjugate base concentration. But he didn't like negatives either. So how do you get rid of a negative log of a quotient? You flip the quotient. You put the A minus on top and the HA on the bottom, and that'll change the sign. So that is where Hasselbalch ended up. So now we call this the Henderson-Hasselbalch equation. And as long as you know the pKa and the concentrations of the conjugate base and the acid, you can calculate the pH of your solution. Notice that with this equation, this helps us understand the best concentrations. Oops, no, excuse me. The best concentrations for these two species in solution, the acid and its conjugate base. Okay. If the conjugate base and the acid are at the same concentration, right, then that's their maximum effectiveness. In other words, if we add base, we got enough of this to work for it. If we add acid, we got enough of that. So if we make them equal to one another, what does this quotient come out to? It comes out to 1. Right? What's the log of 1? It's the power of 10 that equals 1, which is 0. Right? So base 10, this would be 0. So the best pH for your buffer system is one where the weak acid has a pKa near that pH. If you say you want to buffer something at 8.5, right? You want the pKa for the weak acid to be 8.5 or very close to it. Right? Because if that's 0, then these two are equal to one another. That's how we decide what pH is best for our buffer system. All right. So let's see, let me clean this up a little bit. So we can answer this next question. What's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? Right. Notice that this concentration here is 0.45 molar acetic acid, HC2H3O2. And this one is 0.85 molar sodium acetate. Now, does that give us what we want? Well, sure. Put that in solution, it's going to break up into sodium and acetate ions. Sodium's not going to react with anything. It's just a spectator, right? So we're actually dealing with that. What's the pKa? Well, the Ka for acetic acid is 1.8 times 10 to the minus 5 molar. Not molar. It's 1.8 times 10 to the minus 5. So the negative log of that is the negative log of this, which is what? We have to find out. 1.8 exponent negative 5. Take the negative log of that. Let's see, two significant figures, 4.74. Okay, so that goes right here. And this is 0.85 divided by 0.45. Then we take the log of it, the positive log, in there, and then we add that, this value. And I get 5.02. So the pH of that solution is 5.02. Right? If these were actually equal to each other, then the pH would be 4.74. But since they're not, that becomes a modifier. That's a term that we have to add to this one, and we get 5.02 is the pH of that solution. Now, as a general rule, the best buffer range for any system is this pKa plus or minus 1 unit. So we're within 1 unit of 4.74. Okay. And there's animation for that concentration. All right. So the mathematical expression for Henderson-Hasselbalch is A and B. Base divided by acid. What they mean is the conjugate base of the acid. All right, how about electrolytes? What's an electrolyte? Everybody's had blood work analysis, blood analysis, and urinalysis, and they always come out with a list of electrolytes. Right? Those are ions that are present in your blood or in your urine. They're going to be predominantly sodium, potassium, maybe calcium, some magnesium. They have some chlorides, usually. Those are electrolytes, right? But what does that mean in chemistry? Well, in chemistry, the electrolyte is operationally defined. That means it's whatever we want it to be, right? So chemists have agreed that an electrolyte is any substance, when you put it into aqueous solution, will conduct an electric current. Right? Water at room temperature and with relatively low voltage is an insulator. It does not conduct electricity. The only way you can make water conduct electricity, well, there are two ways. You can add an electrolyte to it so you have mobile ions that'll conduct the current from one probe to the other. Or you can run a huge voltage through it, which ionizes the water, and then it'll transfer current. That's why they say if in the lightning storm, don't stand in a puddle of water, because there's enough voltage in that lightning strike that it will go through your body and into the ground, through the water. And of course, your body's full of electrolytes, so you're a good conductor to begin with. All right, so non-electrolytes are those that will not conduct electricity when you put them in solution. Example, table sugar. Why does table sugar not conduct electricity? It goes into solution like that. In fact, you can put so much sugar in solution, table sugar in solution, that there's more sugar than there is water. Right? Make hummingbird feeder juice. Right? A cup of sugar and a cup of water. Right? And it all goes into solution. But it will not conduct electricity because it doesn't produce any mobile ions. Strong electrolytes will conduct electricity very efficiently through that solution. Acids, strong bases, and soluble salts will do that. Weak electrolytes don't conduct electricity efficiently because they don't produce a lot of ions, like acetic acid in vinegar. Right? It doesn't dissociate to a great extent. So it doesn't conduct electricity very efficiently. Those are chemical definition of electrolytes. All right. Here's another concept that is useful if you're working with acids, bases, and electrolytes day in and day out. The concept of the equivalent. The equivalent of an ion is the molar amount of that ion needed to supply 1 mole of positive or negative charge. So what we're saying is, if we have chloride at, say, 1 molar, well, let's say, no, let's do it this way. We can do it that way, but I think it'd be easier to understand if we say we have 1 mole of chloride ions in solution. How many equivalents do we have? We have 1 equivalent because it produces, that 1 mole produces 1 mole of negative charge. Okay? If we have 1 mole of calcium ions, that is 2 equivalents of calcium, because for each 1 mole, it produces two positive charges. We can say the same thing in here for sulfate ions, right? 2 minus charge, that's 2 equivalents. Phosphate ion, 1 mole of phosphate is 3 equivalents of phosphate. Okay, a milli equivalent. What's a milli equivalent? Well, the milli prefix is, you learned it at the very beginning of the semester, a milli is 1,000th of 10 to the minus 3. So a milli equivalent will be 10 to the minus 3 equivalents. No mystery. Okay, when the, I'm not sure if it's reported this way on medical forms or not, that come out of the, have y'all got to that point where you're doing electrolytes yet? You haven't got to that yet, have you? Is that next semester? Okay. I'm just assuming that the reports that you generate for lab work are going to be in this form for electrolytes, milli equivalents per liter. And the reason we use those values, those concentration values, is because it gives you whole numbers. You don't have to deal with decimal fractions or large numbers. Sometimes values are reported as so many grams per deciliter, and for the same reason, just to give us a convenient value. And the doctors are expecting to see that when they get the report. So a milliequivalent per liter. Well, if it were from 1 mole, like sodium, a milliequivalent per liter would be a millimolar. For sodium, that value is 138. 138 milliequivalents per liter. That's also equal to a millimole because it's only one positive charge. So it'd be the same thing as 138 millimole per liter or 138 millimolar. Now, if it's got a charge on it, like calcium is 4 milliequivalents per liter. That's really like calcium. Let's do that as an example. If it's 4 milliequivalents per liter, how did it get there? Well, 2 millimoles of that will give you 4 milliequivalents because it's a 2 positive charge. So it'd be 2 millimole per liter or 2 millimolar. All right. I've gone over, haven't I? Just a little bit. Let me see how much more I got to go. We haven't got the titrations yet. This lab shouldn't take too long. If I can get this done by 11 o'clock, we should be okay. Concentration of calcium ions present in the sample of 5.3 milliequivalents per liter. How many milligrams of calcium ion are present in 180 milliliters of sample? This is a conversion factor problem, a chain conversion. Right? Start off with 180 milliliters. And since our expression is 5.3 milliequivalents per liter, we want that value in units of liters. That's why the first one here, that's why the first one changes the value to liters. Then we can cancel that and find out how many milliequivalents of calcium you get. Right? Then we need to know how many equivalents that is. So you use another conversion factor for equivalents to milliequivalents. There and there. And then you look at what's the conversion factor for moles to equivalents. And for every 1 mole of calcium ions, you get 2 equivalents. That's why the next conversion factor. Now that we've got moles of calcium ions, we can convert that to grams. Right? Use the molar mass of calcium. When calcium loses 2 electrons, does that change its molar mass that much? No, it's in about the 6th position, 7th, 8th position out here. So 40.08 for calcium is perfectly all right. And we get that many grams, but the question is how many milligrams? So we convert grams to milligrams. And we find out that those conditions give us 19 milligrams of calcium ions. Okay. While discussing mixtures of ions, a chemist focuses on ion identity and amount rather than the compounds that supply the ions. The concentration of ions is specified using probably the equivalent. Acid-base titrations. All right. If you haven't heard me say it before, I follow the KISS philosophy. Anybody know what KISS means? Keep it simple, stupid. So titrations, acid-base titrations, are always protons plus hydroxyls yield water. Okay? And these aqueous liquid. So when we're doing the titration, we've got an acid and a base that we're mixing together. And we're going to reach a certain point where we can say this one is equivalent to that one. The amount of this one is equal to the amount of that one. that's a titration. Usually, we know the exact concentration of one of these. And we put a known volume in there. So what do we know? If we know the exact concentration of, say, the acid, and we know the volume that we put in there, we know the number of moles of acid, exact number of moles. Right? And say we don't know the concentration of the base. Right? So we have a concentration of base that's unknown, and we add enough base so that its moles are equal to the acid moles. Right? So this, we know this value right here, and we don't know that value, so we add enough volume so that we know this value. Once we reach a point where they're equal, then we know that one, we can calculate the concentration of the unknown, the base, for this example. Now you can do that with a meter and find out where the equivalence point is, but that takes a lot of time. If you've got to do 100 or 200 of these titrations, you want something that works quicker. So we use an indicator, a color change, right? Something that'll change color when it goes from acid to base or base to acid at the pH very close to where this reaction occurs. So there's some fine tuning that has to take place there so that you use the right indicator. Most of the stuff that we do in student chemistry labs, we use phenolphthalein. Everybody knows phenolphthalein. Changes, if it's acidic, it's clear. And if it's basic, it's pink. And that color change occurs at something in the neighborhood of 8.5 or 9 pH. Phenolphthalein is also good. You used to be able to get it at gag stores. And it come in chewies or chewing gum. And you give it to a friend or maybe even an enemy. And they chew it, and it sends them to the bathroom. Phenolphthalein is very effective laxative, but we don't use it for that. So our setup for titration, and our last lab would have been a titration if the school hadn't chopped out a whole week at the end of the semester. So we lost that one. But you need to know exactly how much of the unknown you're adding. In this scenario, we would have the acid down here, right? A known volume, known concentration, which means a known number of moles. And then we titrate here with this burette until the color changes from clear to pink. And at that point, we know we have added exactly the same number of moles of base as we have acid. And we can do the calculation then. The funny thing about burettes is they're designed to measure delivered amounts. So the zero starts at the top and the larger volume markers are at the bottom. The ones we have here go from 0 to 50 milliliters in 1/10 milliliter increments. Okay. So the thing about this acid-base indicator is the acid-base indicator is also undergoing an acid-base reaction at the same time as your big reaction. It only takes a tiny amount of the indicator to give you a color change. So it doesn't interfere with the major reaction. So when you reach the equivalence point, which is you would have to determine with a pH meter, right? We want the end point, excuse me. We want the end point or the color change to be very close to the equivalence point. And that takes some fine tuning also. So here we have a different indicator. It's changing from yellow to purple. And we probably chose that indicator because it had the color change at exactly the equivalence point or close to the equivalence point of the acid-base reaction. Okay. Now this works if there's one of these and one of these, you can say that. But if you've got an acid that has 2 protons and the base only has 1 hydroxyl, then you've got a different stoichiometry there. So if your acid is like this and your base is like that, the stoichiometry is going to give you 2 sodiums here and 2 waters. So we need 2 of these, right? 2 hydrogens and 2 hydroxyls make 2 waters. 1 sulfate and 2 sodiums make sodium sulfate. So you would have to use a stoichiometry for 1 to 2. So it takes twice as much base as acid to reach the endpoint. That's where the concept, well, there's the calculation. That's where the concept of equivalence comes in. If you're using equivalence, then you don't need that balanced equation. Because if you express the concentration in equivalence, then you've already taken into account the multiple charges on the sulfate ion and the delivery of multiple hydrogens. All right. Let's see. I've run out of time. This is the last one, isn't it? No, it's not. It's not the last one. Well, I don't want to eat up too much of your time. So the answer to this one is 7.03. Solution is neutral, and the hydroxide ion concentration is that. We took this hydronium concentration at 10 to the minus 8th molar. It has a pH of 7.03 there. And it's considered to be neutral because it's very close to 7. It also has a hydroxide ion concentration of, in that case, we would use pH plus POH equals 14. So you find take the pH, subtract it from 14 to give you the POH, and then use negative log of OH equals that value and find out what OH concentration is. And that's what it is, 1.07 times 10 to the minus 7. 25 milliliters of acid requires 14.8 milliliters of 3.351 base for complete neutralization. What's the molarity of the acid? Okay. We assume, in this case, that they're both monoprotic and monobasic, right? Otherwise, we don't know what the answer is. There's not enough information. So in that case, if it's monoprotic acid and monobasic base, then we can equate these two. Molarity of the acid times its volume equals molarity of the base times its volume, and then we can just plug in the values, right? The acid is 25 milliliters. Molarity of the acid is, let's see, we don't know. Molarity of the base is 0.351, and the volume of the base is 14.8 milliliters. Now notice, if we solve for this, right, that puts this milliliters over here. And the milliliters cancel. So we can use the same unit. We don't have to change it to liters. Right? Milliliters cancel. We take 25 into 14.8 times 0.351, and that equals 0.208 molar. That's the molarity of the acid. So you guys will probably get into that maybe next semester in your studies, I assume.